things. Oh, yeah, okay. If there's one theory that nearly everybody thinks is difficult and exotic, it's general relativity. Einstein's 1917 and later contributions. We know general relativity has to be wrong because it is not quantum mechanical. You cannot turn it into a quantum theory. It isn't just that nobody's done it, you can show it can't be done. And if you ask a particle physicist who showed that, he will say, it wasn't me and so I don't care. But you cannot turn GR into a quantum theory, so it must be wrong. And so we often look, GR must fail at some level that will lead us to a better theory, in the same way that the Higgs particle, announced from the Large Hadron Collider last year and given this year's Nobel Prize, we were hoping that it wouldn't be exactly what Peter Higgs had said. It would be enough different to give us a hint of the next level of physics. That hasn't happened. And GR hasn't failed either. As for Higgs, there were several people who actually predicted the particle, and the prize was given to two of them. My actual nomination, if you get to be really old, they ask you to nominate people for the Nobel Prize, knowing you're too old to win. But I nominated Peter Higgs and Tom Kibble, so I got at least half right. But I'm not supposed to tell you that, of course. I'm hoping this will result in the Swedes not asking me again. I've been asked like every year for the last 20 years or something. Yeah, I've got to get one in by February. In any case, we hoped that what was seen at the Large Hadron Collider would not be exactly the Higgs, so it would give us a hint. We keep hoping that GR will fail, but it doesn't. General relativity passes every test you can throw at it, from the 1919 things about the bending of light by the sun, down to modern analyses of the orbits of pulsars. We would like blurring there, and we don't find it. Turbulence and convection, we have no thoughts. Okay, I'm essentially at the end here, but I have to tell you about solitons. A soliton is a wave that propagates without changing its shape. Most waves aren't like that. When they propagate, they blur out. But solitons are different. You can have them in very narrow channels of water. How many of you have been to Loch Ness? Anybody? Loch Ness Monster? You look down from the cliff into the loch. There's a sort of spirally, wavy shape, which I think is what gave rise to the legend. It is, in fact, a soliton wave in the loch. Narrow channels of water make solitons. And this was discovered in 1758 by a chap who was leading a horse along an English canal and dragging a barge. And it was a poor, tired old horse, But all of a sudden, the horse started cheerfully trotting along, pulling the barge faster. The horse had recognized if he pulled at exactly the right speed, the barge moved very easily. The barge was being carried by the soliton wave. This was, in other words, the only scientific discovery ever made by a whole horse. And apparently, the spiral arms that make pictures of galaxies pretty are solitons. That is the quantum mechanical version of making interstellar molecules. The picture is a nuclear physics picture. The reactions are chemistry, and I put stars around you who knows in the interstellar medium. Notice you can make stars with more points than 5. If you're patient, you can make stars with 11 points. That is the laboratory dynamo done with a rotating fluid core. And I assume that's a normal human being standing there to give you the scale. Of course, it might be a Barbie doll, right? In which case the experiment is much smaller. But these are laboratory simulations of dynamos. And at this point, the winds of war begin to blow. Very important X-ray device called a Coolidge tube, built in 1913 by Coolidge. He had to use German glass. That was the only good glass then available. A year later, it was not going to be available to him. And from 1914 onward, making of nitrogen fertilizers, dyestuffs. The chemists of England and the United States had to progress very, very rapidly to replace things that they always just casually bought from Germany. The LA Times the other day had one of its, these interviews with interesting people articles. A guy who makes artificial eyeballs. He uses German glass. We have another World War I, II, III. Going to be the same problem. There'll be no decent glass available here. But the winds of war, Moseley shot at Gallipoli. Einstein moved from Prague to Zurich in 1913, which was very wise of him. An expedition from Germany that was going to look for the bending of light predicted by Einstein in 1914 was in the Crimea and taken prisoner, and death of Karl Schwarzschild. And I think that's it. Bring back some light here. And let me invite questions, comments, rude remarks, or other forms of feedback. Can we get some lights up? Mr. Foster, can we? Yeah. Questions, comments, rude remarks, or other forms of feedback. And you might have to stand up so I can recognize.
We also can get a microphone to people so they can ask their question and other people can hear.
Comments, rude remarks? Yeah, very good.
Why wasn't hafnium discoverable via the Moseley experiment?
Okay. He only went up to gold, which is 59. He didn't quite get there.
Oh, I thought you found everything but that.
The gold's 59, right? And hafnium is 72. I think he just didn't get quite that far. You had to have chemically pure samples for what he did to work, except potassium chloride. You could do both potassium and chlorine, but he didn't get everything because he didn't have sufficiently large samples to make his little plates of some of the heavier elements, I think. What else? Yes?
Did you at one point say that you were related to the Trimbles?
Did I say what to who?
Like Trimbles are your ancestors? Did I miss that in the beginning?
Well, my name is Trimble.
Okay.
And my ancestors on the male side were named Trimble. And they came through Kentucky on their way to Ohio, where great-great-great-great-grandfather became one of the early governors.
And there is a Trimble County, Kentucky, near Cincinnati.
And they were John and James that came through Kentucky on their way to Ohio in the 1700s. And they homesteaded in Ohio, Hillsboro, in 1804. I remember it well, yeah. Okay?
I have a question. You've recounted many scientists in this parade of centenaries and milestones, and I was wondering, which scientist did you find most inspiring for your work or your career?
I do believe my only serious inspiration was the need to make a living. And I suppose my inspiration there was my father, who was a very fine chemist but a rather poor businessman. And between 1946 and 1960, it's 14 years, he had 22 different jobs. He'd be hired by some company to solve a particular problem, and then they'd let him go. And if I came home from school in the middle of the afternoon, and my father's car was in the garage, I knew father had been fired again. And so the idea, my first thought actually was I was going to take the vow, I was going to be a nun. And I realized then never mind. But my second thought was academe. It's almost as safe, maybe these days safer, than a convent. The unemployment rate amongst PhD scientists is very, very small. So I think my inspiration was the need to make a living. That was my father. If you were expecting me to say Richard Feynman, he was a fine fellow. I posed for him when he was learning to draw. If you find enough of his drawings, you'll find some of me from behind. He did very good backs. But some of my fellow graduate students were so good that there was no use trying to compete with them, but I didn't. I figured out a little trail of my own that didn't seriously compete with some of my most outstanding colleagues and peer group, like Martin Rees and Jim Gunn and Malcolm Longair and so forth. Sorry.
It's all right. Any further questions? I have one more. I teach science here. I've had many fine students. I teach science and for general education, astronomy. And I try to tell people what the life of a scientist is like, what we do every day. Mm-hmm. What is a typical day or week for you?
Well, for starters, I have to confess it's a little longer than 40 hours. We have 3 kinds of things we do, at least in academe. One is teaching. I don't particularly like it, that's another issue. But teaching typically takes something like 20 hours a week for whatever you're teaching, because if it's a small class, you've got to learn the subject. If it's a big class, you've got to grade papers. A second component is service to the community. Being on committees, writing proposals, evaluating proposals for NASA and NSF, helping to organize meetings, service, and that's another 20 hours a week. You have the rest of your time to do your own research, which is maybe another 20 hours a week. And so, you know, a typical day is quite often 7 to 7. I'm a morning person, which not all of my colleagues are, but I typically hit the office about 7 o'clock and clear out the email and then go do some things for my class and then do some things in my own research. And in the summer I get to leave when it's still light. In the winter I leave in the dark again. But apart from the teaching, I really do like what I'm doing. Teaching, the real problem is the inexorability. You've got to be there Monday, Wednesday, and Friday.